Okay, so today, children, we are going to continue on our integration journey. Wouldn't it be horrible if I talked like that all the time?
Yeah.
Like that condescending, disgusting, sugary sweet? You can all do this if you just believe in yourself. That ain't gonna happen. Okay, so, yes, no?
Do you know one?
This is not a good way to start a question.
Hello.
Hello, dog. That is an excellent question. But the quiz will be on one.
Yes. Wait. Quiz is one. Thank you.
Okay, so today is going to be a little intimidating, but it's actually a very easy lesson. The intimidating part of it is learning some terminology and some information. But it looks scary, but you'll be okay. I'll help you with it. And when we get to the actual work, it's really easy because you've all done very well in geometry. Yes? Can you find the area of a triangle?
Yeah.
Can you find the area of a rectangle?
Yeah.
Can you find the area of a circle?
Yeah.
Then the lesson will be cakewalk. Okay, but we got to talk about Riemann sums first. So we're going to talk about what a Riemann sum is, who Riemann was, what he did, all that fun stuff. We're going to bring limits back. But hold on, relax. Before anybody jumps out the window, we're just going to talk about how limits affect integrals. We're going to learn about something called a definite integral. We've been doing indefinite integrals, where when you do the antiderivative, you get a family of possible solutions, an infinite number of solutions. We're going to eliminate that and get what's called a definite integral. I'll explain more when we get there. And then, like I said, we're going to use some mad geometry skills to bust out some calculus. Sorry to go street on you there, but that's how I roll. All right, so Riemann, famous mathematician. He comes up, I'm sorry if any of you have problems with this, but that. In case you didn't hear, Drew just summed that up when he said, "Bleh." We're going to do nothing with this except I want you to understand the notation of what's going on here because it's going to allow us to transition into some explanation later on. So that is the area under a curve. Okay? So if you want a picture, here's a picture. Now, before I proceed, what's different about that picture versus what we've done the last 2 days, other than the pretty colors? Ash?
The rectangles are different.
Beautiful. Everything we've done up to this point has been delta x has been consistently the same value. Now all of a sudden I've got a yellow, a blue, a green, and a red that all have different widths. Okay, we'll talk about that in a second. And so this guy Riemann came up with this notation, and delta x is the width of one rectangle. But notice we have different delta x's. I'll address that in a second. F of c sub I is the height of one rectangle.
Totally my fault.
Did you answer? Maybe you want to trip somewhere.
It was an 800 number.
That's what I said. Maybe you want to trip somewhere, or they want to help you. Just give them your social security number. They'll help you. Okay, good. And the sigma, you know that's a capital sigma, right? What is it? Well, I told you. It adds everything up. So what that's saying is I'm going to take a bunch of rectangles from 1 to some number n. I'm going to find the area of each of those rectangles and add them up, which is the same thing we've been doing for the last 2 days. So that's not as scary when you hear it explained to you, right? Now, how are we going to do that? Well, the mechanics become a little bit weird. So Riemann said, what if they're not all, why do I have to make them all the same width? Because we saw yesterday and the day before, if you set the rectangles at a certain width, you sometimes get a lot of wasted area. So you see, even in this picture, that green rectangle is way too wide. I got a whole bunch of wasted space in there. And maybe, depending on the shape of the curve, if I change the width of the rectangles, I would get a more accurate answer. Okay, how are we doing so far? Okay, it's all right. Yeah. Okay, now let's talk about this. So he said the following. Each one of these rectangles is called a partition. I don't know why he just didn't call them rectangles, but he called them partitions. And used delta to represent that. Then he said, okay, let's look at this thing, this notation in red, which is like double absolute value of delta, is the norm of the partition. Okay, so we go back to this picture. Which one is the widest rectangle?
Green.
Green. Okay, so on day one we talked about the idea, if I want my answer to be more accurate, I'm going to shrink the width of the rectangles. Yes? You're with me? Okay, so here's what he noticed. Well, if I take all these rectangles and I pick the biggest one, if I shrink them all at the same rate, and if I focus on the biggest one, by the time the biggest one gets to 0, all the others have gone to 0. Does that make sense? Okay, and that's all. That's all this is going to say, and that involves a limit. So if we denote the biggest rectangle using that weird symbol of the delta inside the double absolute value bars, then if we take the limit as the biggest one goes to 0, by the time we get there, all the other ones will be 0, which means we'll have no wasted space and we'll have an exact answer. Question?
Is this slideshow going to be on? So I can
And I'm not holding you accountable to any of this, but it's important that you understand where this comes from and what Riemann tried to do, or not even tried, what he did. His goal is to get an exact answer, and you'll see there's a process for getting an exact answer that's much easier than this, but before they had that easy method, we needed something else to find the area under the curve as accurately as possible. Okay, so let's back up a second. Are we okay with the concept that as those rectangles get smaller and smaller, our answer will be closer and closer to the actual area under the curve? Is that good? Okay, good. Are we good with the idea that if we shrink the fattest rectangle, then all the others will also shrink down to 0 before the fat one gets down to 0? Right? We're good with that. The notation is not important. The concept is what's important. Okay. So that leads us to a definite integral. And what a definite integral is that value that we're looking for, the exact answer under the curve. And so we have some notation that looks like this. Instead of writing and taking a limit every time, we don't want to bother with that. And this is kind of analogous to what we did with derivatives. If you remember with derivatives, we had that limit of the difference quotient, f of x plus delta x over f, minus f of x all over x, or delta x, whatever it was. And then we said, well, that's ridiculous, let's just use the power rule. So the same thing, instead of using that big scary limit for integrals, we're going to convert to the stuff on the right side. The right side is real simple. It is an antiderivative of f of x from a to b. In other words, what's the area under the curve from a to b? A is our starting point, b is our ending point. And those are called limits of integration. The bottom one is the lower limit, your starting value. B is your upper limit, which is the ending value. And so all those problems that we did the last couple of days, we could go back and rewrite them in this form and say, okay, we want to find the area under the curve from 1 to 4. But the definite integral implies a numerical value, and it also implies an exact numerical value. And like I said, when we first started, that's what we're working towards, is the exact answers. And early on, this is going to be really easy because all we're going to do is some geometry problems. Okay. Good so far? Okay. Not going anywhere. The next couple of slides are all the properties associated with definite integrals. And they're the same properties we've dealt with all along. The integral of a sum is the sum of the integrals. The difference of, or the integral of a difference is the difference of the integrals. Remember, no power rule or quotient rule. We'll get to that in a second. Okay, so let's suppose, before we get into the nitty-gritty, suppose A and B are the same value. Let's suppose we're looking for the integral of some function f from 2 to 2. What's that equal? Well, I guess I should ask, can you find that, not knowing what the function is? Ideas? the value of that integral? What's the area under the curve of some function from 2 to 2? Why is it 0? Yeah, perfect. That's all I was looking for.
Made it more complicated.
Right, so if I would have just asked you,
No, I said I.
what's the area of that rectangle, you would tell me
0.
0, right. But that's too easy. This is calculus.
Yeah.
Right. Okay. That'll come up in some of our identity stuff in a second. Okay, we good with this? Okay. Okay, so there's the plus and minus thing. The integral of a sum is the sum of the integrals. The integral of a difference is the same as the difference of the integrals. A lot of these properties for integrals are the same properties we use for derivatives. Okay, so the first one we use to take the derivative of long polynomials. Instead of doing a whole big thing, we'll just break it into individual parts. Same thing is true with integrals, only with plus and minus, not with multiplication and division. We saw the second one already when we took the antiderivative of something like 3x squared. Just move the 3 out in front, take the antiderivative of x squared, and then multiply your answer by 3. That one we already talked about just a second ago. And going from A to A would always be equal to 0 because it's the area of a segment which has no area. This is new. But if I draw you a picture, I think it would be fairly obvious. Is it obvious now? Maybe it was obvious before I drew the picture. If I want to find the area under the curve from A to B, that would be the same thing as finding the area under the curve from A to C and from C to B. You just break it into 2 regions. So instead of doing this big area, we would do 2 smaller areas. Same thing. Notice the position of C in that. Okay, A to C, where C is on top, then all of a sudden C moves to the bottom because then it becomes the lower limit from C to B. This one is pretty important. When you're setting up a definite integral, the bottom number, the lower limit, should always be smaller than the upper limit. If it's not, you can flip them. Flipping them is fine as long as you put a minus sign in front of it. Okay, so for instance, this would be bad because my lower limit is bigger than my upper limit, so that's the same thing as switching it as long as you put a minus sign out in front of it.
So you don't put the minus sign.
Doesn't matter.
In front of the
Yeah, you can put it in front or in underneath or inside because you can move it out in front. Okay, we good? Okay. What? That's it.
stick this one. Wait, stick this on it will be on this.
Yeah. A little bit. Don't look at me like that. Now we good? All right, moving forward. I'm giving you some information. In a couple more days, you won't need this information, but for this problem, this is almost rudimentary, but I think it's important that you see this. And the same thing is, we did the same thing when we did derivatives. Break it into these really simplistic parts, but then a couple days later, we didn't even need to bother with it. But here, I'll show you how it goes. So suppose we want to evaluate that. A trinomial cubic. Now, if the limits of integration weren't there, if that was an indefinite integral, you'd have no problem. You could find the antiderivative of 10, the antiderivative of 4x, and the antiderivative of negative 3x cubed. However, things are changed now because we have a definite integral. So we want to be able to find the numerical values. And that's one of the big differences that we're going to see. With an indefinite integral, you get a function. With a definite integral, you get a numerical value. So if I just break this puppy into all the different parts, I get this. So this 10 is the same thing as the antiderivative of dx with a 10 out in front, because I can move the constant out in front. The 4x is the same thing as a 4 being out in front with an x dx. And then I just move the negative 3 out in front for the cubic. I know what the cubic is, I know what the x dx is, and I know what the dx is. Plug and chug and get my answer. Anything on that screen bother you?
Yeah.
What?
The antiderivative.
Which antiderivative? There's 6 of them, 7 of them up there. Does the negative 136 not bother anybody? What does that number represent? Area. I have a negative area. Where did I screw up? Or did I? Okay, so this is not, this is going to freak people. I love this one. Okay, so now in calculus, you'll recall in geometry, algebra, advanced algebra, all these other math classes you've taken. Let's talk about geometry, for instance. You're solving a geometry problem, and all of a sudden you solve a quadratic, you get 2 answers, 5 and negative 2. You have to plug the negative 2 back in to see if it gives you any negative answers, because you could never have a negative distance, a negative area, or a negative angle. If you did, you threw that answer out. Welcome to calculus. Now we have a negative area, and yes, that's a real thing. But it's easy. Okay? So, to answer the question, what I would like you to do is get out your graphing device, whether it's your iPad or your calculator, and graph the function 10 plus 4x minus 3x cubed. And see if the picture of the graph can explain to you why I have a negative area. And remember, we're going from only 2 to 4.
What are you distributing? Just don't. What's your natural? Why do I?
All right, so where's the negative number come from? Ben? Below the x-axis, correct. So now, when we're calculating areas under the curve, which is what a definite integral is, anytime it's below the x-axis, we will get a negative area. So it's possible to take an integral and get an answer of 0. Because you would have an upper part above and an upper part below, and if those two cancel out, you get 0. You can get a negative answer, like this one. If the whole thing is below the x-axis, you'll get a negative area. If the whole thing is above the x-axis, you'll get a positive area. All 3 of those are possibilities. Which is what that says. So if I just look at that picture, that's the graph of 2x. from -2 to 1. If I do the integral, for those of you that are visual learners, will that answer be positive or negative? Why? Yeah, there's more area below the x-axis than there is above, so this would be a negative answer. Could you find these areas? How? No, without rectangles. Could you find the exact areas? So could you find that area? Could you find this area? Yeah, they're triangles. Just a quick refresher, you should know those triangles, circles, trapezoids. If you're not good with trapezoids, then break the trapezoids into rectangles and triangles. Okay. No. What's the area? Oh, you mean from the day we're just around? All right, find the area under the curve from 1 to 3 of the function 4. You are all capable of doing this, and in fact, my freshman geometry students could do this. Oh yeah, yeah, I went there. What do you got? Come on. Get her done. Draw a picture. Oh, that might be a good place to start. Stop looking at me in that tone of voice. Oh, I don't know. Start by drawing a picture of the function. By the way, just to make matters worse, you will feel embarrassed when you see the answer to this. And you should be embarrassed. This is ridiculously simple.
This is ridiculously simple.
It's -17.
From where to where? Somebody just asked me, do we find the antiderivative of this? Remember, I said my geometry students could find the answer to this problem.
So no.
Perfect. Go draw a picture up there. Get up there, draw a picture right now.
Go do it.
Do it!
Go, Virginia, go.
Why? I'm just gonna stand there.
Oh, I'm right here.
Okay. Next thing. So like.
Bam. Bam.
Withdraw with well, the same grade. You're getting that minus
I don't know how to use this.
Okay, so this is where you should be embarrassed. What does the graph of 4 look like? It's a horizontal line. If you're looking for the area under the curve of a horizontal line from 1 to 3, that's a width of 2. and a height of 4, and therefore the area under the curve is. Why does it say equals 4?
I'm sorry.
I got it. You're good. You're all good.
Can we make that like the first quiz question of?
That is the entire quiz.
Really?
Right, yeah. I mean, I'm going to change the number. It's not going to be 4. It'll probably be 5. But that'll be one problem.
Write it down, guys.
There would be one problem.
I still don't get it.
Quiet, please. Ask your question again. Yeah. So we're going, the notation says what is the area under the function 4 from 1 to 3? 2 times 4 is 8. 2 wide, 4 high.
Oh, why did you height times width? Yeah. Why did you do 4? So then you get, okay, so you, which one? The top and the bottom is not 4. I'm sorry, it's hard to write on the 4. I don't want like anything, because I don't want to handle it.
Okay. Just because this has been so much fun, let's try another one.
That's not right.
There you go.
We got this.
Four is an actual function, people.
Yes, it is.
What's the area of the triangle? Area base times height.
I don't remember. You didn't give us trapezoid.
Base times.
Can all of you get it all but one? Obviously,
What's trapezoid? Somebody yell at really loud. 1/2 height times base 1 plus base 2. Wow, did I write that 0? Alright, base 1 is 3.
Area of triangle.
Base 2 is 4. Oh, wait. This base is 2. Wait, hold on. This base is 2. This base is 5. So it's 7. No, it's 7 times whatever the height is. This height is something. No,
What is
this base is 8. This base is 2 and 5. So, what's the height? What's the height of the trapezoid? Wait, so 1.5 times 5. So one base is 2, one base is 5. So it's 7 times 5. Because we're
okay, so I'm not going to show you the answer. I'm just going to give you one more problem to chew on. For those of you that got it already, here's a third one. Time to come off the porch and run with the big dogs, kids.
Why is when I try to grab this? I'm sorry, I watched about my calculator.
It's only down to because by definition it's area of the curve of the x-axis.
It's too high. I'm nervous.
So I did half the circle. Oh, it's circle. This is circle 2 pi r. That's because it's pi r squared. So then 1/2 of that is, yeah, you know what's slow?
And also, like, I have
Okay, so stop what you're doing. Here's number 1. We talked about that already. The function 4 is a horizontal line. We're looking for the area from 1 to 3. Done. Second one is a line, and holy guacamole, some of you don't know how to graph a line.
Yeah.
What's the y-intercept of that line? 2. What's the slope? 1. So should it go like this or like this? It go like this, not like this. So when you graph it, you get that shape. What shape is that? Well, it says in big letters. It's a trapezoid. If you don't like trapezoids, it's actually a trapezoid on its side. If you don't like trapezoids, break it into a rectangle and a triangle. You'll get the same answer. What shape is the last one? Semicircle. With a radius of? So, suppose I gave you the function, the absolute value of x. You'll recall that when we did derivatives, we never took the derivative of the absolute value of x. We always just looked at the slopes of that V-shaped thing. The same thing is true here. You will never learn how to, in this class at least, how to take the antiderivative of the absolute value of x. But you can all draw pictures. And the area between the graph of the absolute value of x and the x-axis is a couple of triangles. Find the area of the magenta triangle, find the area of the brown triangle, add them up, you're done. So tonight's work is just geometric figures. Sometimes you'll see the picture. Sometimes, like the 3 examples we tried to do, you'll have to draw your own picture. That's going to be fun. Okay? Problems? There are 2 parts to this lesson. One is the mechanics. Can you find the area of these figures? The other part, and probably the more important part, is understanding what you're doing. Understand the difference between an indefinite integral versus a definite integral. Notice in these other problems that we did, at no point did you have to go back through the process we did before. I wasn't looking for 1/2 x squared plus 2x as the antiderivative. That's not how this stuff works. We'll get to that, but that comes later. A definite integral, in other words, an integral with numbers on the top and bottom, will always give you a numerical value. An indefinite integral gives you a function. They're different animals. Got it? Beautiful. We're all done for today. So tomorrow, we'll talk a little bit more about this. You have a quiz on Monday, and Tuesday in class, you have an activity that I will help you with to help you understand stuff. Okay? If you are not going to be here next week, you need to complete that stuff before you leave, and Thanksgiving weekend is a no homework weekend. Therefore, you will get no homework from me, hence the reason you need to take your quiz and do that activity prior to leaving. Noah.
Are these days like directly lined up with how much school we've had? Like, is this after like the 60th day of school?
No, it is not. I screwed up a couple things along the way. Day is day 60, which on the calendar is not Thursday's homework, it's Wednesday's because we're still a day behind. We will be caught up after Thanksgiving break. Also, I need your day 59 homework, please.
May I go to the bathroom?
Yes.